Okay, this is lecture 38, and so in this lecture I'm going to talk about the Gillespie algorithm, which is basically an algorithm to actually see and visualize the realizations from a stochastic model. Okay, so let me just remind you about a continuous time Markov chain in general, and so we're going to think about all the different aspects of the continuous time Markov chain when we try to figure out how to actually simulate it. So remember the evolution of continuous time Markov chain. We basically think about if we're in state I, then what happens from state I? So if you're in state I, you stay in state I for a certain period of time until basically this alarm clock goes off. So once the alarm clock goes off, then you move to another state, and you move to the state in which the alarm clock goes off first. So each of you have these transition rates, Q1J, Q2J, etc., so you have the transition rates QJI, and then you move as soon as the first one goes off. So remember how to calculate the holding time. So you're going to go when the first alarm clock goes off. So this is a minimum of a bunch of exponential random variables. So remember how you calculate that. Basically your holding time is going to be the sum of all of these transition rates, where K is just all of the different states that you can transition to from state I. So keep this in mind when we're actually going to talk about the Gillespie algorithm. Okay, so now what's the probability of transitioning from a certain state? So you need to know how long you're going to stay in a state if you're wanting to simulate this. You also need to know which state you're going to go to. So how do you code which state you're going to go to? Well, remember, you want to figure out the probability of going to state J by just looking at the rate QJI, so the rate at which you go from state I to state J, divided by the sum of all of the rates that you can get to from all of the different states. So if I can go from I to K, and there's a bunch of these, I'm going to sum up all those rates. This basically gives me that holding time, right? The mean of that holding time, or the parameter for the holding time. And then I'm going to take my QJI, this transition rate from state I to state J, and divide it by that. Okay, so how do you visualize a potential path for continuous time Markov chain? The way that a lot of people do it is they do use the Gillespie algorithm. So this is one method. There's many other methods. Gillespie algorithm, one of the bad things about this one is it's a little bit slower than some of the other methods. But for all of the models that we're going to be doing in this course, that's not a big problem. So you're not going to have to worry about going too slow or your code going too slow in the models that you're going to do in this course. And so just to give you a kind of a heads up about the different methods out there, some of the methods are called like tail leaping. And so instead of in the Gillespie algorithm, what we're going to do is we're going to consider one transition at a time. So when is the next transition going to take place, and where does it go? What you can do in a method called like tail leaping is you can consider, if I take a longer period of time, how many transitions would I have made, and where would I have likely gone in all of that period of time. So it's that's why it's called tail leaping, because you're basically leaping over a bunch of transactions. So you can imagine why this would be faster than just going one transaction at a time. But for our purposes, we're going to consider the Gillespie algorithm and that algorithm only in this course. Okay, so let me give you a summary of the Gillespie algorithm, and then we can go from there. Okay, so the first thing that you're going to do, as you normally would do, is figure out where you're at initially. So initialize the state of the system. If you're talking about a population, how many people do you already have in the system? So initialize your state, and then for each state of the system, calculate transition rates. So you want to calculate all these transition rates going from I to J. You want to know what those are. And then you need to calculate the sum of those, because remember that's going to help us with our holding time to figure out how long we're going to stay there. So we're going to simulate the time to the next transition by taking that draw from an exponential distribution. So we're going to stay in a certain state for a certain period of time, and then we're going to transition to another state. So what we have to know when we're doing these simulations is, one, how long are we going to stay there, and two, where are we going to go? So the next thing is to simulate which state is coming next. What is the transition type? And then we want to update the time. So we've stayed this certain period of time, so now we're at a new time. Update that time, and then basically we're going to iterate this until we get to the maximum time that we want. However long we want to look. If you want to look at 30 days, you want to look at 1 hour, you want to look at a year, you just keep on going. Okay, so the nice thing about Matlab is you have a lot of capability in terms of estimating. You have a lot of capability in terms of basically coding math, and so it's a really nice tool for that. Problem is it requires lots of packages. So we want to take a draw from an exponential distribution, and there is a way of doing this with a command called exprnd. So this is basically taking a draw from an exponential. So you basically want an exponential random variable, where the exprnd stands for. Not all people will have that. So some of the packages aren't available on certain Matlab programs. If you just get the basic Matlab, it's not going to have this. But even if you use Python or some other language, it may not have a draw from an exponential distribution. But most likely, you can draw from a uniform distribution. So one of the nice theorems is how you actually take a draw from a uniform distribution and you can get any other random variable that you want from any other distribution. So if you let u be a uniform random variable on the interval 0 to 1, and t is some other random variable satisfying some other distribution, then you can say t is equal to f inverse of u, where f is the CDF of the random variable t. So if t is drawn from an exponential distribution, then the CDF of this t is basically this. So if you go back and look at exponential random distributions, look at what the cumulative distribution function looks like, and it has this form where you have a parameter lambda. So the way that I can do this is basically I can take a draw from a uniform random variable, and I could think about sticking it in here, but I need to take the inverse of that first. So if I take the inverse of this, I'm going to have basically natural log of t divided by lambda, and I'm going to evaluate this at my random variable u. So this is how you actually get a draw from an exponential distribution using a uniform random variable. If you use the exprnd command, if you're able to do that, then all you have to do is exprnd and in parentheses put what your parameter is, what your rate is, what your lambda is that you're using. Okay, so for our example in this lecture, we're going to consider a simple case. It's called a birth and death process, but it's called a simple birth and death process. So remember, this is our general birth and death process. It has you can either go up, you can go down, or you stay the same, and it's really a small probability that you're going to do anything else. But we're going to consider this rate lambda I to basically be some parameter b times I, which is I is the number where you're at now. So if x of t is I now, currently, then my lambda I is going to be a function of basically how many people or where I'm at in my state times some number b. And similarly, my mu is going to be basically some proportion of my I. So some proportion, you can think about some proportion are going to die, some proportion are going to move on, etc., etc. So this is the kind of the way that you can think about it. So a simple birth and death basically has just these simple rates for lambda I and mu I. Okay, so now we want to simulate this using the Gillespie algorithm. So this is a code. It's given on D2L under the file name ssabirthdeath.m. So I'm going to kind of walk you through the different parts of this code. This is Gillespie algorithm for that. So first of all, you initialize the state of the system. So remember, you have all this stuff up here. What is all this? It just gets your computer ready to handle everything. So it closes all the figures, gets rid of all the variables that you would have had, and clears the screen. So now I'm going to initialize the state. So basically this says that I'm going to assume that there's basically 5 in my population already. And then what's the second step of the Gillespie algorithm? Well, the second step is way down here, is to calculate the transition rate as QJI. So here I have to initialize my B and my D, because remember this is a simple birth, simple death. So I need to know what B is. So here I'm going to just assume that there's a slightly more birth than there is death. So this is slightly larger than this is. I'm going to go for 10 time units, and I want to plot 20 sample realizations. So I want 20 samples in my plot. So this is just for the desired samples. And so for each sample, I just basically want to start over. So this is kind of how I start over. This is a while statement. So basically, I want to keep going until I reach my maximum time, and as long as my population is above 0. So I'm assuming that if I'm at 0, I can't come back from that. So I'm assuming 0 is an absorbing state. So I only want to keep on going if I don't die off first. So this just increases the count. But this is the part that actually calculates the transitions. So I have RB, which is the birth rate, the probability of a birth, and RD is the probability of a death. The next step in my Gillespie algorithm is to calculate the sum. Remember, I need the sum in order to think about when I'm going to transition from one state to the other. So the sum of all my transitions rates, I'm just going to have RB plus RD. Okay, so I'm going to keep on going. The next thing I do in my Gillespie algorithm is I simulate the time to the next transition. So here on this one, I'm assuming that I cannot use the command exp_rnd. I take a uniform random variable, and I basically take the negative log. Remember, okay, in Matlab, this is the natural log. If I do log, it's the natural log in Matlab. It's kind of confusing because log everywhere else is base 10, but this is natural log in Matlab. So I'm going to do log of my random variable that I've drawn, divided by my capital R. Remember, this is the sum of all of my transition rates. So then the next thing that I'm going to do is I'm going to simulate what's going to happen next. So this is kind of like if you remember coin tossing. What do? You have a random number, right? And I want to know what's going to happen. So if my random number is less than my RB over R, so remember I only had 2 possible transitions here. So if my RU2, my random number, is less than my birth rate divided by the sum of all my rates, then I'm going to have a birth, so I'm going to increase the count by 1. Otherwise, I'm going to have a death, so I'm going to decrease the count by 1. What's next is I'm going to update my time, and I'm going to iterate 2 through 6 until the final time, so that was what the loop was for. So I'm going to keep on going until my count is either 0 or my time is up, and then this part is just to plot it. Remember, this n comes from the fact that I want to do this multiple times to look at the different realizations. And this is what I get. So these are all the different kind of sample paths. This is what I would have gotten if I had a simple birth-death model using an ODE. Okay, so the next time we're going to do a couple more examples, a little bit more involved examples, and go from there.